Hi, my name is Alexandra Henriquez, and today I'll be talking to you about diffraction techniques, methods of probing atomic structure. In today's module, we'll be trying to answer four main questions. 1. Why are diffraction and scattering techniques used? 2. What are diffraction techniques? 3. How are the experiments conducted? And 4. What data do we obtain? In answering the first question, why are diffraction and scattering techniques used, there's a number of reasons why they are advantageous. First, the main reason is that they give structural information at a small length scale. Moreover, they can be used to obtain average structure and local structure information. This information can be used to determine chemical composition, phases of the material and fractional amounts of these phases, texture of a thin film, microstrain, atomic positions, defects, and many other factors. Also, in situ experiments are possible with many diffraction techniques. These techniques generally are considered non-destructive in that they do not damage the sample in the process of collecting this data. They have varying complexity depending on the need of the experimenter, and it usually does not require special sample preparation. So if you have a powder sample, you can use that. If you have a bulk sample, you can use that as well. It can be used for thin films and a variety of material conformations. The second question, what are diffraction techniques? The general idea is it is an experimental method involving the elastic scattering of an incident beam. Now, this incident beam can be photons, generally at the X-ray wavelength, electrons, or neutrons. The X-ray scattering is what I'll generally be focusing on in this presentation. In this experiment, an incident beam interacts with atoms in a material, and that beam is diffracted at specific angles. Those angles are dependent on what you see in the figure on the right, which is Bragg's law. If Bragg's condition is met, then there is constructive interference of the incident waves, and you get a measured signal. Measuring the diffracted X-rays gives information about chemical composition, crystalline structure, defects, etc., as mentioned previously. Now, how are the experiments conducted? What you see in the image on the right is a traditional laboratory scale X-ray diffractometer. On the left side, an X-ray tube generates the X-rays that constitute our incident beam. These X-rays are directed at the sample, and that sample diffracts those X-rays. The X-rays are then collected at the detector on the right. Now in the figure, you'll see mention of a shutter, a monochromator, slits, etc. This has to do with the specification of this instrument and the optics that are used, and they can vary from diffractometer to diffractometer. In any X-ray diffractometer, the source, the detector, and even the sample can move depending on the equipment. So sometimes you'll have the X-ray tube and detector moving, sometimes it'll just be the X-ray detector, and sometimes the sample will move as well, depending on the needs of the experiment, of course. Now, in carrying out diffraction experiments, you don't need to do this exclusively with a lab X-ray source. If you need higher energy, shorter wavelength X-rays, these experiments would typically be conducted at a synchrotron facility. The image shown on the bottom right is the Advanced Photon Source, or APS, at Argonne National Laboratory, just outside of Chicago, Illinois. This facility is one of the several synchrotron facilities that exist in the world. In addition to X-rays, I mentioned previously that neutrons and electrons can be used. If you want to conduct a neutron diffraction experiment, this would typically be done at a facility such as the Spallation Neutron Source, or SNS, at Oak Ridge National Laboratory, shown in the image on the bottom left. If you would like to conduct an electron diffraction experiment, this kind of measurement would typically be done in an electron microscope. Now let's talk a little bit about our final question. What is the data that we obtain? You may have noticed the image on the left previously in the presentation showing an incident beam, a sample with different orientations of grains, and finally, a diffraction cone. Now, these cones, when projected onto a two-dimensional screen, give rings, as shown in the center image. When you take this projection and take a linear slice from it, you obtain an image like the one on the right, showing what people traditionally think of when they think of X-ray diffraction data, which is an XRD profile with peaks and a little bit of background noise, showing 2 theta versus intensity. This line profile can then be taken and the peaks can be identified and directly associated with lattice planes in a crystal structure, as shown in this central image, with the 111 plane highlighted in yellow on the left, the 200 planes parallel to one another shown in the center, and the 220 planes shown parallel to one another on the right. Now, this data that we obtain often needs to be processed more than just peak identification. If you're looking for more specific information, full pattern profile fitting can be done using methods such as the Rietveld refinement method. Additionally, researchers here at NC State have been working on using a Bayesian method to fit a full pattern profile or individual peak fitting done with the line profile analysis software, or LIPRIS, that was developed here. In conclusion, X-ray, neutron, and electron diffraction techniques are useful for elemental, molecular, and structural materials characterization. The experiments can be tailored specifically and give extensive information. A diffraction pattern is obtained, and data processing can yield information about atomic spacing, vacancies, phases, and much more.